Okay, so in this problem, we're going to prove that 1 times 2 times 3 plus 2 times 3 plus 4, 3 times 4 times 5, and so on. And any statement that's in this form, n plus 1, n plus 2. So the product of 3 consecutive integers, and the sum of all those up to any term, is equal to this sum. So, and on 4, n plus 1, n plus 2, n plus 3. So that's what we need to prove, that that's true for any number n. Positive number n. So, showing true for n is equal to 1. So we substitute 1 in, and it just gives us that first statement, which would be 6. Substitute 1 into this statement, so 1 on 4, 1 plus 1, 1 plus 2, 1 plus 3. And doing our calculation gives us 6. Bingo. True for n is equal to 1. Happy days. That's nice. It works for n is equal to 1. And it should if it's doing it. If it doesn't, then well, it's disproved. So our assumption is it's true for any number n is equal to k. Any positive whole number, it's going to be true for. So this statement here is true for this statement here, which is okay. This is what we want. Now, what we're looking to prove in the next one, if it's true for n is equal to k plus 1, what we want to do is substitute k plus 1 into all those. So what we're looking to be required to prove would be the k plus 1 on 4. And then we'll have a k plus 1 plus 1. A k plus 1 plus 2. And k plus 1 plus 3. So we're going to have that. So, or if you want to write it as k plus 1 over 4, or even a quarter of lots of k plus 1, k plus 2, k plus 3, k plus 4. That's what we want to get in the end. When we start off with this statement, which was everything up to the k term, and then when n is equal to k plus 1, we go one step further. So we have the k plus 1, k plus 2, k plus 3. We had k before we had n was equal to k, now we've got n is equal to k plus 1. So there's the n plus 1, n plus 2, and k plus 1 is replacing n. So, keeping that in mind, what we want to find at the end. We need to firstly get rid of this statement because it's got unknown terms in it. But we do know that statement there, from our assumption, is equal to this part there. We know that's true because we assumed that in our last part. So again, we're using what we know is true. Not what we don't know is true, but what we know is to be true, because we've assumed that's to be true. And then we've got the k plus 1th term added on there. So again, what do we need to factorise out? Well, let's have a look. We said look for our factorisation when we can. So again, what's common? The k plus 1, k plus 2, k plus 3 is common to all. That's okay. We can take those out. There's k plus 1, k plus 2, k plus 3. And what we've still got to get out, we wanted a quarter out the front. So we got our quarter there, and we factorise a quarter out of 1, which gives us our 4. And all we're left was the k in the first part, because everything else got factorised. The quarter, k plus 1, k plus 2, k plus 3. And what we're left with was just the 1 factorised a quarter out, which left us the 4, which left us our k plus 4, which is our statement that we actually wanted to prove. There's our quarter of k plus 1, k plus 2, k plus 3, k plus 4. So we have proved it. So that's what we needed to prove, which is very nice. So when we're looking to prove statements, we keep in mind what we require to prove. Then we write our statement, our step 4 as usual. Because it was true for 1, it must be true for 2, and it must be true for 3, and then so on for all positive values.